How are we doing? Organic Chemistry 1, Chem 230. This time we are with Chapter 9. We're almost done, guys. I know it's been a long way. Things are getting busier and even with more content in these last chapters. Chapter 9 will be adding a few more reactions to our already long list of chemical reactions. Now we will be dealing with alkynes. Alkynes are those functional groups, as we know, that they are the triple bonds, right? So we have 2 pi bonds. If on chapter 8 we were talking about pi bonds being very nucleophilic because of the electron density, excess electron density that is present in alkenes, you can more or less imagine what is happening with alkynes, in which we have 2 pi bonds, right? So we're expecting that alkynes should be even more reactive than alkenes. Okay, so let's see how we do. Chapter 9, alkynes. This chapter covers, just to give you an overview, covers the foundations, right, of alkynes. I'll give you a brief introduction of what alkynes, right, represent in nature, naming of alkynes, preparation of alkynes, and then we will also be discussing the reactions of alkynes. Okay, so and then it's very good that we are starting this type of sequence of right for a particular functional group, because that's more or less what you guys will start seeing on Chemistry 240, Organic Chemistry 2. So for example, in a particular chapter, you will be doing, let's say, alcohols. You will see background of alcohols, naming of alcohols, preparation of alcohols, and then reaction with alcohols. Then the next chapter is going to be about amines. It will be the same thing, background of amines, where we found them, importance of amines, preparation of amines, and reactivity of amines. Okay, so every chapter we have about, from now on, every chapter will have the same breakdown. Okay, so let's get used to it, and then let's get ahead with alkynes. So let's see what alkynes have for us. So as we know, the overview for alkynes is that they are very nucleophilic. They have a lot of electron density. Remember that a pi bond is formed by 2 p orbitals. Right here we have a p orbital. Right here I'm circling the p orbital, and they have a pi bond. Let's say that this one is the py, right? And there is a second p orbital that is overlapping, that is a cross, and then let's say that this one is px. Right? So we have electron density, and you can imagine that this triple bond, like a cylinder, is a cylinder that goes around the sigma bond. So it's well covered. That particular sigma bond is very, very strong. And then, of course, as a product of this, those 2 pi bonds, we can expect that the distance between these 2 carbons is going to be extremely short. Okay, so because remember, every pi bond is a through space, right? Covalent bond. So definitely the closer it gets, the stronger the bond is going to be, and also the shorter is going to be the length, right, of the bond. Yep. So what else to say about triple bonds? Triple bonds are found in nature very rarely because of the reactivity. As we mentioned before, for alkenes, that pi sigma electron repulsion creates that alkenes are highly reactive. You can imagine alkynes. It's really, really rare to see alkynes. Where do we find alkynes in nature? Pheromones. Pheromones are these molecules that are secreted by animals, plants. I mean, it is different. Any living organism will secrete when it's time for mating, right? So for reproductive purposes, animals will start secreting these molecules. And of course, they're going to be secreting it as alert, right, for the opposite sex, right, to be attracted. So like as a signal that is going to be time for mating. Those pheromones contain many of them, they contain alkynes. Why alkynes? Because they are very specific. They are not that common, right? Functional groups, they are very important, but they also have a short life. You don't want to be, right? I mean, those animals, they don't want to be secreting this. So anywhere they go, they will be chased by, right, for mating, right? So it makes sense that alkynes, since they're very reactive, they're exposed to air, to water, right, to any other substance, and maybe sunlight, they get degraded, they get decomposed. So the pheromone only has a short lasting effect, right? It makes sense because once again, you don't want to be day, night, right? In the morning, next morning, the next night to be like releasing these pheromones and then being around you. So And then in the industry, where do we find alkynes? Well, I'll tell you one that has very important applications, which is the stronger, or is this compound, HC=CH. This is called acetylene. Why is it important, Professor? Well, here in this particular chapter, we will use it for a lot of synthetic application. At the very end of this chapter, we will use it for synthesis. But in industry, acetylene is one of the most powerful gases. It's the gas that gives you the hottest flame that right now we have in nature, right? Of course, we can use different combinations to maximize the power of a flame, right? The fire. But acetylene is of course, it's always going to be part of that combination. What is that? Because it has that pi bond, those two pi bonds. So the combustion of these pi bonds, of course, it will release a lot of energy in the form of heat and light. Okay, so those in welding, you have seen like these guys, they have these torches, right? Or maybe in the movies, in the Star Wars movies or any sci-fi movies, you have seen that normally they try to escape from the monster, or they try to escape from the aliens. And normally they say, seal the door. And they have these torches, right, that seal and weld the metal. So the animals, whatever it is they're being chased for, they don't really come to you. So that torch, that is acetylene. Is that light? That's why they say, like, don't look at that light because it really makes you blind. That is true, because it is not only heat, but it's also light in the form of little high radiation, which could be UV, X-rays, is secreted by that particular combustion, right, of acetylene. So the application of acetylene as an alkyne that is used as a gas is a gas. Acetylene is a gas. They don't use it for domestic because it's too much energy. It might even melt your pots and your, right? I mean, anything that your kettles, everything can get melted by this fire, this high temperature. It has a really high temperature for acetylene. Okay, so let's continue. Nomenclature of alkynes and steps. So this, I mean, at least a UPAC, right? The International Union of Pure and Applied Chemists has done a favor to us, right? By having these rules that they apply to everything. So the same rules that we apply for alkanes and alkenes, for example, identify your longest continuous chain, number the chain according to the, right, to the proximity to the substituents, or start naming the substituents by the alphabet, right? Give priorities depending on the number, depending on the proximity, right? That type of rules, they apply to any functional group, so including alkynes. Okay, so the only thing that we have to keep in mind for alkynes is the ending, right? Alkanes, they end in ane, right? So for example, pentane, hexane, heptane. Alkenes, they end in ene, pentene, heptene, butene, propene. Alkynes, they end in ine, meaning that now we will be talking about butane, hexane, ethine, propine, right? So all those, that could be the ending for alkynes. Okay, so now between alkenes and alkynes, which one has priority? Alkenes have a priority. Okay, so does that make sense, Professor? Because the triple bond looks like more complex, looks like more reactive. It should be more. No, unfortunately, no. So a UPAC follows the rule. Remember the alphabet, they love alphabet. So between in and ein, these two endings, the in by alphabet is before the y. So that's why alkene has priority over ein. Is it really just by alphabet? It doesn't really depend on the property. Apparently, since these compounds are unsaturated, yeah, by the way, that's how we call these compounds, unsaturated compounds, alkenes and alkynes, because they have double bonds, they have pi bonds, right? So saturated compounds, they have very similar properties. As we will see, alkynes and alkenes, they share many of the properties, same reactivity. We will see here hydration, here we will see ozonolysis, here we will see hydrohalogenation, hydrogenation, all the same reactivity, same reactions. So that's why maybe the UPAC decided, no, let's put them in the same bucket, alkenes and alkynes, and then let's just separate them according to the alphabet. That's why alkenes, they get a higher priority than alkynes, okay? So that is in the case of a tie. So let's do some examples here. Pentane, pentene, pentyne, right? So we're familiar with this naming. We used the first two for the previous chapter, chapter 8. Now we have pentyne, which is a triple bond. The numbering, we start numbering here, 1, 2, 3, 4, 5. Something very important that you notice, hopefully you guys notice in this structure, is that alkynes are never bent, right? So it is wrong if you guys write a triple bond like that. We should not write it like this. That would be wrong, because remember the hybridization for sp, right? The hybridization for this carbon for triple bonded is sp, and the bond angle for sp is 180 degrees. So it has to be as linear as possible when you show it in the structure. Am I gonna get points off if I bend it? Yes, you're gonna get points off if you bend a triple bond. So if you guys show me this as pentyne, 1, 2, 3, 4, 5, then I would say like, no, I don't know that molecule. What is that? To me, it looks like a dragon or something, you know, or like a worm that is a snake. To me, it will be everything except pentyne. I'm just thinking that, I mean, it will be something. This one is a biology class that you're trying to represent, maybe you know, something else, right? So that is not, don't bend it. You just have to show it straight. And you can see it here. For example, heptyne is right here. Heptyne, it is, you can see that the triple bond is straight. So it has to be shown like that. Okay, so your longest continuous chain should contain the triple bond. What if I have double bonds and triple bonds in my molecule? Okay, so choose the longest continuous chain that contains as many unsaturations as you have, meaning that as many double and triple bonds that you have in your compound. Okay, so this next is going to be identified and name the substituents as we have done it, right? All these chapters, and then you're going to assign the numbering. The numbering, it is always, right? If you have substituents, for example, here you have these substituents, and then you have a triple bond. Of course, the triple bond gets priority over the substituents, right? So for example, in this case, 1, 2, alkyne, 1, 2, methyl. Which one wins? The alkyne. The alkyne gets priority over the substituent. So always get the end that is closer to the alkyne. Okay. The local number is the number 1, not 2. Where? Okay, it's only one number. Yeah, that is, I was misreading this. It's saying that the alkyne, you only use the number of the first carbon of the alkyne, right? So for example, the alkyne here goes 2, 3, but you don't have to say 2, 3. You only say 2. So in this case, it could be 2 heptyne. Right? That would be the parent, right? The backbone of my compound. And of course, it has some substituents, right? So 5,5,6 trimethyl 2-heptyne. Okay, so 5,5,6 trimethyl 2-heptyne. In this case, we can also break up, right? The name of heptyne, and I can introduce the number in between. Okay, so that's here are some common names. Acetylene is used as a core. Is used as a very, very common way how to use common names, but I would say like we're always using a UPAC, so don't really get used to these common names because there is more things to memorize. I'm sure that you guys don't want to memorize more at this point, right? So let's do some examples for naming naming of alkynes. Okay, so in alkynes, let's say that I have this compound. They tell me name this compound. I have to identify my longest continuous chain. I can see that my longest continuous chain is right here. Is the horizontal. So I have here 1, 2 substituents. 1, I have the alkyne. Therefore, my numbering will start with the alkyne. Okay. Now substituents, methyl, methyl, methyl. That's all I have. So it would be 3, 4, 4 trimethyl. Okay. Anything else? No, that's it. Then my backbone is going to be called 1 pentyne. That will be the name. Can we omit the number 1, right? So like, remember like in alkenes, we were saying that, okay, so if you omit the number 1, you have to assume that it is position number 1. Technically, yes. So you say 3, 3, 4 trimethyl pentyne. But I would recommend you, I mean, to be honest, for our quizzes and exams, just put the 1. I know it is an extra number and dashes, right? But it's better to specify the number, right? The location for the alkyne. The good thing of alkynes is that they don't have EZ. There is no cis strands, right? Because they have only one. There's only one branch on the right, on the right, and one on the left, right? So that's the great advantage for alkynes. We don't have to be concerned about RS or any EZ cis strands for alkynes. Okay, so let's do one that has double bonds and triple bonds. Okay, so let's see this compound. Let's put here chlorine and here. Okay. So longest continuous chain. So I can see that my longest continuous chain is right here. I'm just gonna shade it. Okay, that's my longest continuous chain, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 1, 2, 3, 4, 5, 6, 7, 8. No, I want to maximize my unsaturations, right, on my longest continuous chain. So I go by that one that is shaded, right, in gray. Now I have to number it. 1, 2, 3, double bond. 1, 2, 3, triple bond. So between double and triple bond, we say that double bond wins, right? So it's the one that beats the alkyne. So I should say 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so is it because of the alkene or is it because of the substituent? Because here you say like, oh, 1, 2 substituent. Here, 1, 2, 3. Yeah, but here you give priority, right? So between the substituent and the alkene, which one is priority? This one is number 2. This one is number 3, right? Which one wins? Alkenes, definitely they win. Okay, over substituents. The alkene is an actual functional group, so it's more important than the methyl group. Okay, so after that, so let's see. I have the number. Let's do substituents. On number 4, I have a chloro. On number 5, I have an ethyl. Right? On number 9, I have a methyl. Good. So if we keep naming, so let's see what we have by alphabet. The chloro should be first. So I will call it 4-chloro. 5-ethyl. 9-methyl. Okay, and now here, pay attention. Here, between the two, which one should I name first, right? In the backbone, should I start with the alkene or with the alkyne? According to the alphabet, in comes first. So the backbone is going to be named with the alkene first, because it's in before ein, right? In before ein. So here is decane, right? Dec, because it's 10, dec. So if it's dec, so I will call the decene first. So where is my alkene? My alkene is on carbon number 3. 3-decene. In 7 ein. Okay, the alkene gets named first on the backbone. On the backbone, the dec is because of the 10 carbons. It's 10 carbons, right? 1, 2, all the way through 10. The 3 means that the alkene is number 3. Can I call it dec 3 in? Yes, you can do that, right? It will be dec 3 in 7 ein. Okay, so that's an option as well. Okay. Can I have multiple triple bonds? Yes, definitely. You can have as many triple bonds as you want. I'm gonna make this substituent so you don't forget it. We haven't used it in a while. Okay, this compound, now we have to name it. Longest continuous chain, I can see my longest continuous chain right here. I start numbering right on this carbon. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 carbons. Substituents, I have bromo, nitro. Don't forget this substituent, please. It's very important. And here I have a methyl. Okay, bromo, nitro, methyl. So bromo wins in alphabet, then methyl, and then nitro. Okay, so the name would be, oh, I forgot here the EZ of the alkene. I'll come back here in a minute. Okay, so here, let's see, 5-bromo, 4-methyl, 4-nitro. Okay, now the name of the alkynes. 1,6 1,6 octadiene. Diene. No, it's diene. Yeah, here is diene. Okay, so 1,6 octadiene. Right, so it's because of the ending. Yep. So that would be the name for this compound. Di, because you have two alkynes, right? Diene. Yep. So that would be the name 1,6 because my alkyne is carbon number 1 and then carbon number 6. Okay, let's come back here. I know that easy is chapter 8 about alkenes, but here we have one. So here my substituents, right? So here for this carbon, my highest priority is right here, the chlorine, right? Chlorine beats carbon. And here is carbon and hydrogen, of course. Carbon is more important. So here, my two highest priorities are cis. Therefore, it's going to be C alkene. Professor, do I have to say that it is number 3? No, because it's your only alkene. Alkynes, they don't have EZ. So if you mention Z, of course, it has to apply to the alkene, and you only have one alkene. So you don't have to mention the number here. Okay, Z for chloro, 5-ethyl, 9-methyl, 3-decene, 7-ion. Okay? So that will be the name for this compound. Are we going to have also alkynes in triple bonds? Even though they are very rare, they are not that stable, but we can technically, on paper, you can get many things. So alkenes in this case will be cyclohexane. Sorry, my bad. Hexane. In this case, I don't need to say 1 cyclohexane. What if I have the same but with substituents? Okay, the alkyne gets priority, of course. So 1, 2, 3, 4, 5, 6. Right? So then I would call it 3,3-dimethyl cyclohexadiene. Sorry, cyclohexane. So I have to say 1? No, because in rings, at least in rings is more straightforward. Rings definitely the number 1 should be the most important group. So cyclohexane should be the name for this compound. If you want to write the 1, it's not wrong, but I mean it's redundant. Okay. All right. So that's about naming. Definitely we'll have more examples later. Remember that I always post solve problem videos, and you can always go back to Blackboard to reinforce, right, more this particular concept. But also in the additional resources, I have videos from other authors, other let's say partners. I mean, people that also work in organic chemistry that they post their videos about tutorials. Definitely, please take some minutes. I know that this semester, I mean, we've been watching about 20+ hours, right, from YouTube or these tutorials, but I mean, that's the way how, I mean, the best way is just by learning. Reading is the only way how we can get used to it and solving problems, of course. Okay, so what else comes about background of alkynes? It's about the classification. Alkynes can be classified as terminal or internal. Terminal means that the alkyne is, right, it's at the end, right? It's one of the edges. And internal means that the alkyne has 2 carbon sides. So here the terminal has 1 hydrogen. That hydrogen is going to be very important. A terminal alkyne is extremely important for reactivity purposes and also for synthesis. Okay, so the internal, no, that's okay. I mean, the internal is not as important because it has two carbon chains. So basically they prevent the reactivity. The reactivity of an alkyne really resides on that H. That H is extremely crucial for alkynes. Of course, the triple bond is also, right? The 2 pi bonds is also important, but that H gives an extra reactivity to alkynes in the case of terminal alkynes. How can we express it? What is it like? What is that reactivity? That particular property that we're mentioning for alkynes is the acidity. Acidity of terminal alkynes. Terminal alkynes are unusually acidic. Normal alkanes like ethane has a pK of 50. Very, very base. I mean, it's not base, it's not acidic at all. It's pK of 50. Just to give you an idea, water has a pK of 14. pK of 14 means that water, imagine water is way more acidic than alkanes, like 10 to the 30 36 times more, right? So it's more acidic. And if you taste water, it's not acidic at all, right? I mean, pure water. Ethylene, which is an alkene, is 44. It's slightly more acidic. But alkynes, they are way greater, right? So they're way more acidic. Why is that, right? So go back to chapter 3, right? If you go to Ario, right? If you go to acidity, acid and bases, there is a topic about the O. The O is about orbital, right? The sp hybridization that is present in these particular carbons, these two carbons are under sp hybridization. They are extremely unusually acidic. Why? Because that orbital is electronegative. Why is it electronegative? Because sp is composed of 50% s character and 50% p character. Why is that important? Because s character are smaller orbitals. They are very small and they are very close to the nucleus. Since they are very close to the nucleus, they are really attracted to the nucleus. Because remember, all the protons are in the nucleus. So the s orbital contains electrons that are strongly attached to the nucleus. They are very difficult to, right, to go away or to run away from the nucleus. That's why that orbital is electronegative, because it's really attracted to the nucleus. So the more S character you have, of course, the more you will have those properties. That's why sp is more acidic, is more electronegative than sp2 and sp3. So here in alkanes is 50 because it has very small S character, sp3, only 25%. In sp2, you have 33%, but in sp, you have 50%, right? So you can see how the acidity increases. That is, I mean, if you want to go more details, you're going to get more details about the acidity. Please go back to chapter 3, the video about orbital, and definitely you will find the answer about, I mean, more detail about the sp character and the importance in acidity of hydrogens that are attached to sp carbons. Okay, so what we need to know for this chapter 9 is that to remember that the pKa of alkynes is 25, which is unusually acidic. Acidic compared to organic compounds, right? So we're expecting a pKa of 50, not 25. Is twice as acidic, right? I mean, it's 25 times, 10 to the 25 times more acidic than a conventional ethane. So even though it's 10 to the 20, pKa 25, it's not as acidic, right? As we said, the water even has a pKa of 14, so it's not acidic. I mean, it's acidic in the organic chemistry context, but in reality, it's not acidic. So even though it's a stronger acid, but we need as a good base to deprotonate it. For example, here, a strong base is sodium amide. Okay, so just for now, I'm just going to be very clear. The only base that we are using to deprotonate an alkyne, a terminal alkyne, is going to be sodium amide. Okay, sodium amide. I will spell it here. Sodium amide. Okay. What if I use sodium hydroxide? I forget and I write sodium hydroxide. No. The second equation is telling you that you write sodium hydroxide with an alkyne, terminal alkyne, is not going to deprotonate it. So sodium hydroxide is not basic enough to deprotonate an alkyne. What if I use potassium hydroxide? Potassium hydroxide could be, I mean, it's really, really rare. I mean, it has to be under very extreme conditions. You have to apply heat or something like that. So it's kind of unusual. So the most common base that is used to deprotonate an alkyne is sodium amide. Okay, so depending on some experimental conditions, you can use potassium or sodium hydroxide, but in general, for our lectures, we will use sodium amide. Okay, so don't use sodium hydroxide, don't use potassium hydroxide. Technically, it is sodium amide. In practice, could be something different, but at least on the paper, we will use only sodium amide. Okay, so as you can see, remember the equilibrium always favors the weaker acid. Here in this case, my weaker acid has a pKa of 38. That's why the equilibrium shifts to the right side, leading to the deprotonation of the alkyne. If you use the second one, the second combination, sodium hydroxide and the alkyne, then you will produce a weaker acid. So that's my weaker acid, 25, versus water that has a pKa of 15.7. Well, I said 14, but it's about the value. So the equilibrium will favor the weaker acid, which in this case is the alkyne. I don't want that, right? I want to deprotonate it. So it is not favorable, that process. Okay, so don't use sodium hydroxide. So use sodium amide, sodium amide. Okay, so remember sodium amide. And so what you're gonna produce if you deprotonate the alkyne is something called alkynite ion. It comes from alkyne, right? Alkynite ion. This alkynate ion is very nucleophilic. I know that it is not in the list of our nucleophiles, right, that we use on chapter 7a. Remember in 7a we had a table with strong nucleophiles, weak nucleophiles. We don't recall seeing the alkynate ion, the alkynate ion in that list. But now I'm telling you that alkynate ions are strong nucleophiles. Okay, so you can even add it to the list of 7a for your nucleophiles. Sodium amide, that's the formula. NaNH2 is often used as a base, but others can be used as well. What are those others? You can also use hydride ions, namely sodium hydride. It can be used to deprotonate that particular alkyne. There's some more. I mean, here there's a list. What can I use to deprotonate the alkyne? You can use any of these guys that I'm circling: the hydride, the amide, and of course the alkane anions can be also used. You guys haven't seen these compounds yet. You haven't seen the chemistry of these compounds. That's coming in organic chemistry too. Alkanes can also be deprotonated under very extreme conditions. I mean, very strong basic conditions. You can deprotonate an alkane, and the base that you generate is very powerful. That compound is called the Grignard. You guys will see it. Just remember, oh, Professor Navarro told us about this Grignard reagent. Grignard. Okay, Grignard reagent, that's how you guys will start producing. How can I make those? You will make it with metals. You use lithium, magnesium, and then that's how you produce a Grignard reagent. But we don't use Grignard reagents in CHE230. We're only going to use hydrides, for example, sodium hydride, NaH, or amides, so NaNH2. Those are suitable bases that you can use to deprotonate an alkyne. Right? You can see that terburoxide cannot be used, ethoxide cannot be used, hydroxides, they cannot be used. They are too weak to deprotonate an alkyne. Okay? So that's why only use sodium amide and sodium hydride if you want to use any alternative bases. Okay, so now how do we make alkynes, right? So now that we know the properties, now we're ready to, I mean, I know how to name them. If I see them on the paper, I'm able to see, I'm able to give a name. Now how to make it. So the only way how you're gonna make alkynes is from dihalides. Dihalides are, I mean, you guys have synthesized dihalides in chapter 8, right? There is, remember, there is a reaction between alkenes and bromine or chlorine, and you can get two, we call it vicinal, right? Vicinal halides, which are neighboring, adjacent halides. So you can definitely make them by elimination reaction. Here we will go back to chapter 7b to do elimination reaction. So for example, in the first reaction, you can see an alkyl halide, which is a substrate, and you do an elimination reaction. That's an E2 reaction. The E2 reaction, the strong base will take the hydrogen. This one comes as a double bond and the bromine leaves, giving you the alkene. But if you have a dihalide, you guys will have two bromines. And of course, you need an adjacent two hydrogens. So this guy, the one that I'm circling in blue, will be eliminated with this hydrogen, giving you one alkene. And then in a second elimination reaction, you guys can eliminate this bromine here in yellow with this hydrogen here in yellow. That's how you produce an alkyne. Okay, so you have a double elimination. Is that under E2 reaction? I mean, they call it E2 reaction, but it should be very different because here, as they will show it here in this scheme, they're doing an E2 reaction, but here is an E2 reaction on an alkene. How can an alkene adopt the anti-coplanar configuration? Yeah, that's really not, that's something that is kind of like unclear, that an alkene adopts the anti-coplanar, right, transition state. It's impossible. An alkene is flat, is still planar. But in theory, I mean, they have proposed that, yeah, let's say that it's E2 because this mechanism is not fully understood yet. Okay, so in the very first, you have a geminal dihalide. Geminal dihalide means that the halide is located on the same, right, on the same carbon of the substrate. So here, this bromine will be eliminated with this hydrogen, right? This one that I'm crossing will be eliminated with this one, and you get this alkene, which is an intermediate. And then that alkene then gets another dose of base. That base now removes this hydrogen, and then this bromine goes away, giving you the alkyne. You can do it with geminal dihalides or vicinal dihalides. The vicinal dihalides, the bromines are adjacent, are neighboring. Right? And you also have two hydrogens, right? Definitely you need hydrogens. If you don't have hydrogens, there is no way you can make an alkyne. And use a strong base. What strong base can you use? Once again, the only strong base that we will use with alkynes is sodium amide. Can I use sodium hydride? Yes, you can use sodium hydride, but nothing else. And here it tells you that excess equivalents of sodium amide are used to shift the equilibrium towards the elimination products. So if you have this compound, definitely you can, right? This one is a geminal dihalide. Geminal dihalides with excess sodium amide in ammonia. Ammonia is a solvent. It will give you the terminal alkyne in this particular case. But you need to, that's an issue, that whenever you guys are making a terminal alkyne, you have to protonate it. Why? Because remember that alkyl alkyne that you're producing will be in the presence of excess amide. So it will be deprotonated, giving you the alkyne ion. You don't want the alkyne ion, you want the alkyne. Then you have to protonate it. That's why you do a second workup with water to protonate it. Okay, so that's really the synthesis that we will do. I mean, how to produce the alkyne. So here is an example. Right? So here you have a vicinal. No, it's not vicinal. It's geminal dihalide. And here I have two hydrogens. One hydrogen here, one hydrogen here. So this bromine will get eliminated with hydrogen, and then this bromine gets eliminated with this hydrogen. What do I use? I use excess sodium amide. But I notice that what I'm producing is a terminal alkyne. Why is a terminal alkyne? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But since this guy is terminal, in the excess of amide, it's not going to produce that. It's going to produce the alkyne ion. I don't want the alkyne ion. That's why in a second step, they use water to protonate it. And then that's how you produce your neutral alkyne. Right? So let's do that explanation on paper, because I think that that's way better. Okay, synthesis of alkynes. Okay, so let's say that I have this compound, and I have bromine, two bromines. Okay, and then I treat it with sodium amide, NH2 minus, excess sodium amide, excess. Okay, so, and then they tell me, okay, write the mechanism for this conversion. Excess. Okay, great. So what I'm gonna do here is the mechanism, right? I know that it is through E2 reaction. So I will have the first one. I'm gonna pick that carbon. Can I pick any of the? Yeah. Remember that the alkyne is formed between two carbons. It can be on the left or can be on the right. So here I have two hydrogens. The first base is gonna take the electrons from the hydrogen. This one comes down and this one is out. Of course, that is anti-coplanar, right? So it's an elimination reaction. The first product, or the intermediate that you guys will get, is a double bond here, bromine and hydrogen. And here, technically, you guys will add excess amide. Now, this one is not anti-coplanar. How can it be? But it happens. That's why this mechanism is not clearly understood. They say that it's E2 reaction. Some authors say that, but it is not anti-coplanar. So definitely something else should be happening. It's only that it's not that clear till this point. Okay, so I produce that alkyne, which is this alkyne. That's the mechanism. Now, why am I not adding water here? I don't need it because I'm not producing a terminal alkyne. This one is an internal alkyne. So you produce internal alkynes, you guys don't need to add water. No water needed because it's internal alkyne. Okay, but if I make a terminal alkyne, that's a separate story. And I'll show you why. Because you guys have this compound, bromine. Let's do with a bisphenol. Okay, so that one comes with a hydrogen, and this one has another hydrogen. Right? So if they tell me, okay, eliminate it with amide, so the amide will take this hydrogen, this bond comes down here, and this bromine is out, right? That one I will believe it that is an E2. That one definitely. To me, it does look like an E2. You form the first alkene. Now they say that you add excess of amide for a second E2. Yeah, here, I mean, it looks like anticoplanar, but remember this is flat. It's really not 3D. So I don't know about the anticoplanar. To me, anticoplanar means that I have to be able to do a Newman projection, right? Okay, but let's just listen to the authors and then let's just do an E2 reaction. Bling, bling, right? Goes, triple bond. Now here, what happens here? I do produce that, right? Because if you count 1, 2, 3, 4, 1, 2, 3, 4, and then between 1 and 2, I have a triple bond. But remember that you guys are in excess of amide. Right? That H is there. I'm in excess of amide. So definitely I will have more amide than needed. So that alkyne will definitely get deprotonated. I didn't mean to deprotonate it. I know that you didn't mean to deprotonate it, but it is in excess of amide. Excess of amide deprotonates no matter what the alkyne. So what you really have at the end of your synthesis is this one, the alkynide, the alkynide ion. Alkynide ion or alkynide anion, right? As we call it. That's the end product. So what should I do to, I don't want this. I want the actual, like the neutral alkyne. Then that's when you add water in step 2. But you have to carefully put the label 1, excess amide, step 1, and step 2, water. And that water is going to protonate the amide. Sorry, the alkyne ion. Now it's neutral plus OH. Can I use acid? H3O plus? Yes, you can also use acid. Can I use sulfuric acid? Yeah, you can use sulfuric acid. Not concentrated. Concentrated is not needed. But H3O plus, if you write H3O plus, that works. That's good. Water, that works. That's fine. Can I use ethanol, methanol? Yes, technically yes, but I mean, they are not really that common to see in chemical reactions, right? I mean, if we follow the pKa's, yes, ethanol, methanol, because they are more acidic. They're more acidic than alkynes. So definitely the equilibrium should drive it towards this side. But commonly, I just tell you what I see more often, that to protonate an alkyne ion, alkynide ion, they normally use water or H3O plus. And you only do this, only use water or H3O plus if you are making a terminal alkyne. Okay, you are making an internal alkyne, water is not needed. An H3O plus, water or H3O plus are not needed. Right? So keep that in mind. This is just like here I'm going over the mechanism, right? Mechanism for deprotonation and synthesis preparation of the alkynes. Okay, so remember that. That's the mechanism. Do we need to know the mechanism for this double elimination? Yes, we need to know the mechanism for this double elimination. Okay. Do I have to show anticoplanar, antiperiplanar, do the Newman projections for this? No, just the same mechanism as I show you in my previous example. Okay, so you want to take a break right now? I mean, that would be a good opportunity because now we're going to be moving on to the reactions. 12 reactions, they look like a lot. I know that I promised you guys that it will be way less on chapter 9 compared to chapter 8. But here we have a lot of duplicates. So for example, these two are really one reaction. 2 and 3 is only one reaction. This is also only one reaction. hydrogenation. Yeah, these are all three part of one single reaction. Okay, so don't be scared by the number 12. And most of them, they're very repetitive. Most of them are a repetition. Okay, now since we have this list in front of us, right? I mean, hopefully, I mean, you guys are back now from your break. I will tell you which ones are the ones that we need to know the mechanism. So to know the mechanism, we need the mechanism of the alkylation. Okay, I'll write here, mechanisms. What mechanisms do we need to know? We need to know the previous, right? The elimination, right? I mean, the preparation, how we prepared it. And I don't know, how many do you guys want? Guess, give me a number. I don't have any, oh, here, the acid catalyzed hydration. Oh, no, here there will be at some point when we study this, there will be something called the enol keto tautomerization. That one I need you guys to know. That one's gonna help you a lot for the next class, chemistry 240. Okay, so there, when we do reactions 4 and 5, you guys will see something called the enol keto tautomerization. So that mechanism we need to know. In addition to the elimination, right, the number 1, which is the one that I just did for you, right? Elimination using geminal dihalide or vicinal dihalide. That's that one we did. And then the alkylation, definitely that one we need to know, the alkylation. Okay, the other ones, no. The other ones we don't need to know the mechanisms. Okay? So only 3 mechanisms for this particular chapter. Okay, so let's start with the easiest one. Okay, so ready for the reactions. I know we're starting from the end, but let's see. The first reaction is the catalytic hydrogenation. Catalytic hydrogenation is exactly the same thing that we saw for alkenes, right? Remember H2PD, H2PT. It's exactly the same. Here, this hydrogenation reduces, is a reduction reaction, like oxidation reduction, but in this case it will be a reduction reaction, and it converts your alkyne into an alkene. Okay, so H2PT converts or produce alkanes. That's one way how to make alkanes, H2PT. Okay, so is there any, here I'm going all the way from alkene to alkane. Is there any way I can stop at alkene, right? Because alkene is the intermediate, right? It should be somewhere in between. From triple bond to single bond, there should be one stage in which it goes to double bond, right? Before going to single bond. Yes, there is. But this reaction is so violent, is so aggressive, is so complete, is so reactive that it goes all the way. Oh, what if I use maybe 1 mole, 1 to 1 mole? Can I control it? Maybe if I control the temperature, if I control the pressure, can I right, like slow down the reaction, make it less selective? No, if you use H2PT, it goes all the way to alkane, no matter what you do or what reaction conditions you apply. Okay, so catalytic hydrogenation, H2PT, H2PD, they always go all the way to alkanes. Do I have to be concerned about the cis strands? No, in this case, no, because you have a triple bond. Triple bonds, they only have 1 branch each side. It's not like the alkene that you can have 2 branches. Then you are, in that case, you're concerned about cis and trans. Here, you are not concerned about cis and trans. So here, you're only concerned about the alkene. Let's go all the way to alkane. Now, that was a big concern for organic chemists, that you go all the way to alkane. They wanted to investigate about ways how to stop at alkene. I don't want to reduce it all the way. I just want to stop halfway, which is the alkene stage. Yes, so they produced, they wanted to do intermediate, right? Because as you can see here, the alkyne first is reduced to a cis alkene, which makes sense. But that cis alkene in the presence of H2PD or H2PT also gets reduced again to alkane. So that's why they noticed that it doesn't really stop, right? You cannot isolate it because your product is also reactant for the same reaction. So there was no way how to do it. So what they did is that they say like, okay, we have to come up with something. We want to make the alkene for this reaction. So they did something very smart, and then that's when this scientist came, Linglar. Linglar is a scientist that definitely worked with this particular reaction, and he tried to poison a catalyst. Okay, so what is a poison catalyst? He also used PD, right? We know that PD, that is the catalyst, right, for this reaction. Remember, you can use H2PD or H2PT, palladium or platinum. He started adding some combinations to try to block, to inhibit the reaction that goes all the way to alkanes. So we here tried different mixtures, palladium, some heavy metals, some solvents, and then he came up with this particular combination. It's a cocktail which includes different reagents. Quinoline is an organic component. It's basically a base. Palladium, barium sulfate, and methanol. Methanol is, I guess, is the solvent, right? It's the solvent for the reaction. Okay, so and P2 and I2. Okay, that's another one. This is another catalyst, but linear catalyst is the mostly known for this particular reaction. Okay, so if you want to stop an alkene without going to the alkane, then you have to use the linear catalyst. But alkanes can be two ways, cis and trans. What type of alkene is this producing? This one is producing the cis. So you guys want to produce the cis alkene from an alkyne, you have to use hydrogen in Linglar's catalyst. You have to include the hydrogen. If you only put Linglar catalyst, that's incomplete. You have to put H2 and Linglar's catalyst. Now, what is this poisoning, Professor? I mean, how does that work, the poisoning? Yeah, the poisoning really works. And then here, I'm sure that the poisoning compound is the barium. Barium, and then most of the heavy metals, as that is the action, really, how all these heavy metals work in your body. Why are they so toxic in your body, right? So why is lead so bad? Why is arsenic, chromium, manganese, cadmium, right? Mercury, why are they so bad? Because their charge, the charge of these ions and also their size make them very interactive with enzymes in our body. Enzymes and really good receptors, cell receptors that we have in our body, right? So what happens with those? So what happens is that these heavy metals, those metals that have that charge, they occupy the active site of the enzymes. As you guys know, that enzymes are also catalysts. So they block your enzyme. So your enzyme, instead of being invested in doing, let's say, glycolysis, or maybe be invested in do any isomerization, right? Or any, let's say, degradation of oxygen or transportation. Let's say the hemo group, right? The hemo group is blocked with, let's say, carbon monoxide, right? Then that hemo group is useless. So your enzymes, they lose their activity. So without the enzymes, you guys cannot produce your food. You cannot produce energy. You cannot do any physiological functions, right? So that is the action of a poison, to decrease the activity of your catalyst, your enzymes. The same thing happens with the linear catalyst. He noticed that palladium is an excellent catalyst because of the surface. So he was thinking, okay, so why don't we just damage the surface of palladium a little bit? So it's not as effective. So it doesn't go all the way to alkane. Let's change it. So he started adding barium sulfate. So he noticed that barium sulfate alters, right, changes the surface of the palladium. So barium binds to the palladium, and then it inhibits that reaction of the alkyne. So the alkyne only goes to alkene, but then the alkene to alkane doesn't happen because of the poison catalyst. Okay, so that presence of barium, that's why barium, by the way, barium is very toxic. I know that we use it as a contrast agent for some imaging purposes, but it's very small doses. If you guys are exposed to barium for a long time, and then at high concentrations, it's very toxic. So it creates this barium sulfate salt, which is highly insoluble, and they can really clog your arteries and veins. So you will die of a heart attack or something. And then anybody will just say like, oh, what was the reason of his death, his or her death? A stroke or something, but really that person was poisoned, right? So that's why I like a lot of the forensic science. I mean, the forensic files, these videos, CSI, because they really go over like different ways how a person can be poisoned. The barium sulfate is one of the cleanest. Why? Because barium, nobody would even imagine. The periodic table right now has about 117 elements. How can you imagine that element? Let me see, barium. Barium is 56. How can you imagine that element 56 was responsible for a death? You will have to go one by one to see if that is what is the reason of the particular poisoning. So nobody would imagine barium. Another poison that is very common is thallium. Thallium is another poison that nobody would ever imagine, but thallium is lethal. It's highly controlled in chemistry labs. Another one, arsenic. I mean, we know arsenic already. Another one that is very toxic, bismuth. Bismuth is also very toxic. Okay, so there are many elements. I mean, that's one thing that chemists. I mean, we as chemists we know what are the elements that are crucial. I mean, the good and the bad. I mean, it's good to be a chemist in the sense that you know things, but you also have a lot of responsibility. And then we as scientists also have that particular mindset that we have to use what we learn for good. I mean, you guys know how to extract caffeine, right? So you guys did a lab for caffeine extraction. But does that mean that I can extract any alkaloids? Yes, you can extract any alkaloid using the same principle. Okay, so does that mean that I can extract anything, some other things? Yes, you can extract it. Now, am I gonna do it? No, of course not, because I know that it's wrong, right? So you want to extract some other alkaloids from other plants or the green plants, of course, I mean, you know that it's not legal. So we have the tools, we have the skills, but it depends on you, depends on us, I mean, how we use it, okay? That's also, I mean, something that I just wanted to share with you, something, I mean, now that I'm here with the lecture, that was the idea for the atomic bomb, right? So something that humanity regrets that happened in 1930. I mean, the Hiroshima and Nagasaki happened in 1945. That happened right when Einstein was in the top of his studies. He was one of the most famous scientists. His idea for the nuclear power, nuclear plants, right, about radioactivity, was really to use it for nuclear plants, right, for energy production, for disinfection. That was the real idea of Einstein. But what happened? Some other people, they use it for atomic bombs, right? That wasn't his idea. So Einstein was really sad when he saw that his theory, his studies were used to destroy. Okay, so humanity, they change things. Scientists, we don't really mean to create something for bad applications, but people, they find the way. So for example, if I show you guys how to extract caffeine and how to identify it, of course, I mean, you have the power now, you have the ethics, you have the mindset, you have everything with you. So now it's up to you. I mean, all chemists we are. I have known many cases, many. It's very sad to see that some of my colleagues from one of the schools, they went to jail. Definitely, they went to jail because they were applying their knowledge to bad stuff. So very reputable people that they really are behind bars right now because they use their skills the wrong way. Okay, so that's a parenthesis. The poison catalyst, right? Catalyzes the poisons here. Here's the step is catalyzed, right? The first addition is catalyzed, but the second one is not catalyzed, so it makes it very slow. That's what happens with the poison catalyst, is that it affects only partial, it's poison, but it's not killed, right? So even though this reaction has two steps, one to alkene and then to alkane, so apparently that linear catalyst only affects the second step. It's not catalyzed, but the first one works perfect. Apparently that mixture, quinoline, barium sulfate and methanol, doesn't affect the first reduction, but the second reduction is affected. That's why it doesn't go all the way. Now, what if I want to make the transalkene, right? So the transalkene, that one is done with sodium, metal sodium, no sodium hydroxide, no sodium chloride, metal sodium, elemental sodium. Elemental sodium in liquid ammonia. It has to be liquid. Don't forget the liquid. This reaction have to be written as you see them here. So it has a high yield, 80%. Of course, you will get, I mean, that is the maximum. It's a stereoselective. It's not specific, it's selective. You get 80% of the transalkene. Okay? So are we gonna know this? We're gonna learn this reaction. That reaction is really a radical reaction. That's chapter 9. That's the next chapter. But even in that chapter, we're not really gonna go over this reaction. Okay, so I'm just letting you know that this reaction goes through radicals, chapter 10. But even in chapter 10, we will know the study here. Okay? But they give you a transalkene. Does it go to alkane? No, never goes to alkane. Never. That is not observed. This alkane is not observed. It stops at alkene. There is nothing poison, so that's how the reaction works. Has to be it. This one is a good summary for the reduction, the hydrogenation. Linear, right? You have the alkyne, the linear catalyst stops in cis alkene. If you use sodium and liquid ammonia, transalkene. If you want to go all the way, yeah, you can use H2PT and give you alkane. Here, the transalkene, also H2PT, it give you the alkane. What if I don't want to stop? I just want to go all the way. You want to go all the way, just use straight H2PT. Right? Remember the H2PT or H2PD, right? Which is the palladium or the platinum alternatives. Okay, good for alkynes. So that is the reduction. So far we covered already. We covered hydrogenation. We covered already metal reduction. And we cover poison catalyst. See? So 3 reactions in one, we're already done. Okay, next, hydrohalogenation. The same strategy here, actually, this slide is showing you how we did it on chapter 8, right? We had an HX with an alkene, and the alkene, it follows Markovnikov. In alkynes, it will also follow Markovnikov. Okay? So you see the alkyne, there is a Markovnikov, sorry, it's an HX, and then that's Markovnikov 60 to 80%. Now, that is if you add only 1 mole. If you add excess, you get it twice. Are both of them going to be Markovnikov? Yes. This reaction is 100% Markovnikov. So you guys will get the geminal dihalide. Only if you guys see excess, okay? Now, let's make an arrangement. Now, do you guys want to see the excess word, or do you guys prefer to see the 1 mole word? So I would say that I will write on the exam excess, okay? By saying excess HX, meaning that you guys have to do all the way, right? Go all the way. Maybe in some of the previously posted practice exams, all exams, I use the word 1 mole here, right? To represent that I'm doing like a stoichiometric, right, relationship. But now, just please, just look at the answer key for those, and then just apply whatever the answer key tells you. But from now on, I mean, with you guys, starting with you guys, I will basically write the word excess, okay? If you just see HX alone, that means that it's a 1-to-1 ratio. So 1-to-1 ratio if you only see HX. If you see the word excess, that means that you have to use a lot of it, right? So do all the way in the case of alkynes, okay? So agreed? Okay, so you see some old exams, old quizzes. Oh, professor, in exam 2017, you have HX and you did everything. You went all the way. Yeah, that's why I'm telling you guys right now is that starting here, now with this video with you guys, I'm telling you that from now on, I'm going to be using the word excess. If you see HX, that means it's a 1-to-1 ratio. To do excess, you have to see the, it has to be written excess. Sometimes I will abbreviate it with excess, which is phonetically is the same, excess, like extra small, and then that's we will go all the way, right? Geminal dihalide, remember, is Markovnikov. What to do if you guys have, right, something. Now let's change. I'm gonna stop sharing. What if I don't have the Markovnikov, right? Remember that was also an issue for when we were doing alkenes. Let's say that I have this one, and I do HX, HCl. If I do HCl, which one is my Markovnikov side? Both of them are Markovnikov, right? One branch, one branch. Then in this case, I will get this. Actually, I will get four products. It's kind of interesting, this one. Because I get cis and trans, right? And then I will get the other one. Oh, my bad. Eraser. Okay. In this case, I will get 4 products. Why? 2 in the bromine here. Why 2? Because I will get cis and trans, right? So here, no cis and trans, I will be E and Z. If you look at this alkene will be Z, and this one will be E. C and E adding to this carbon. And here is the Z and E using this carbon. Okay? You see, this 2 is using this carbon. And this 2 is using this carbon. But I will produce the E and Z isomer. Okay, so that, oh, I know. Professor, why are you putting Br if you put Cl? Okay, so we change here. HBr. You will get 4 potential products here. Okay, what if I use excess? If you get excess, then you will be doing fully here and fully here. Okay? Meaning that 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. So this carbon, 1, 2, 3, 1, 2, 3, this carbon. And then this one will be this carbon. I will get bromines here, 2 bromines, plus 2 bromines here. Because remember, it's excess, right? Because both carbons are Markovnikov. That's why we'll get two products in this case, if I do excess HBr. So if I do only one, I will get here easy and here easy. Because both of them are Markovnikov. Here, both of them are Markovnikov. That's why I get here excess here and excess here. Okay. So that's what they tell you also on the right on the slide. Here, here they're not showing because it's terminal. They don't have really easy, but here this alkene definitely will have, right? In this case, you have H's. That's why it's not important if you guys have right, easy because you have H's. But if you have a different other natures, definitely you will have the complex stereochemistry. So I'll show you my picture. Okay, that is the proposed mechanisms. We don't need to know the mechanism for this reaction, but just to give you an idea, normally in alkenes, we know that hydrohalogenation will potentially give you rearrangement. Why are we not seeing rearrangement in alkynes? They were trying to propose, right? Why there is no rearrangement? Because there is no carbocations. How can you determine, how do you know that there are no carbocations? How can we explain it? There should be an alternative mechanism, right? That does not produce carbocations. And this is what they are producing. They're saying that the HX attacks twice simultaneously to the alkyne. So 1 to 1 carbon and then the other one to the pi bond. So it forms a transition state that prevents the carbocation formation. Otherwise, you will have a migration and you don't have migration. It's possible that several variances says here that many mechanisms, they are not 100% sure about this mechanism. You will say, like, oh, well, professor, but why are organic chemists so lazy that they don't know the mechanism right now? I know this reaction has been around for at least a century and they still haven't figured out what is the mechanism. Yeah, definitely. Once we come up with a microscope or a high definition microscope that can see atoms, right? At that particular size, 10 to the minus 10, then you will see how a reaction goes. So far, we haven't achieved that size. Once we can look at the molecules at their actual size, that will be great because millions of questions will be answered. Millions and millions of questions will be answered. Not only mechanisms, also in bio, physics will be fully enriched with that if we have such a microscope. Okay, so we also have the hydrohalogenation and anti-Markovnikov, the one that is with peroxides, right? So remember that in this case, can we use excess? Yeah, you can also use excess. Here they are using only the one, right? Only the 1-to-1 ratio, 1 mole of this, 1 mole of the alkyne, and you guys get an E and Z isomers, right? Makes sense because you get the DBr per one side and on the other side, up and down. We can call it like that. 82%, a mixture of the E and Z isomer. Is there any major product, minor product? Does it go by stereo, right? Stereo hindrance, anything? No, you just get a mixture, technically 50-50. Why 50-50? Because I mean, always one, I would think that the trans would be major product compared to the, right, to the cis. Technically, yes, but on the paper, let's just say that you get a racemic mixture. But technically, yes. So if you tell me like, oh, but trans should have less acidic hindrance, so it should affect the reaction somewhat. Yes, but the percentages don't really, right, are not like that dramatically different. This only work with HBr, okay? So you are working with alkynes, HBr and peroxide, no HCl and no HI. And of course, no HF. That is a radical mechanism that covered in chapter 10. Yes, that one we will do it. Maybe not with alkynes, but we will do the reaction with alkenes, right? Which is what we study on chapter 10. So that one we are definitely gonna do on chapter 10, which is the next and last chapter. Okay, dihalides, right? So that's the next reaction. Let's go back. So you see, in a very short time, we already finished this. Hydrohalogenation, 2 equivalents. Hydrohalogenation, 1 equivalent. So far we are the elimination is the preparation. We already did it. So we have only few. Right now we're about to do these two, halogenation or dihalogenation. Okay, let's go back. Dihalogenation. Very similar concept. We don't need to know the mechanism. Hydrohalogenation. Dihalogenation. No, this is not halogenation. My bad. This is just as a summary, right? It's a summary of how to do the halogenation of the alkyne. If you use excess HX, you get the geminal dihalide, and then that one can go back to the alkyne if you do elimination, right? Double elimination, for example. That is the one way how to convert from alkyl halide, dihalides, and alkynes, going both ways. If you want to go to dihalide, use the alkyne with excess HX. And if you want to go from the dihalide back to the alkyne, you just do the double elimination with sodium amide and water. Okay, great. So that would be another good time to take a break because now we will do a hydration of alkynes. All right, next we have the hydration of alkynes. The hydration of alkynes, if we recall from alkenes, right? We have 3 types in alkenes: acid catalyzed, oxymercuration, and hydroboration. In this particular case, we only have 2 types, only the acid catalyzed, which is the Markovnikov, right? And then we will have the other one, which is the hydroboration. We can call it also hydroboration, that is anti-Markovnikov. Okay, so at least that one has a lot of similarities with the alkenes that we saw in chapter 8. So acid catalyzed Markovnikov, and then the hydroboration is going to be anti-Markovnikov. So what happens? We don't need to know the mechanism of the conversion reaction. Only the last stage, this part, right? That's the one that we have to understand the mechanism. Okay, so for this reaction, you guys will have the alkyne, which is a triple bond. You will use this combination of reagents: sulfuric acid, water, and mercury sulfate. Okay, so is it acting the same way with the mercury sulfate, right? So as the one that we saw with the mercurium ion that prevents the carbocations, very similar. So definitely the mercury is going to be involved, right? It will involve in the production of the Markovnikov, right, reagent. Okay, so here it will slow the reaction, the result from the formation of binary carbocation. So yes, so by telling you that the mercury sulfate will slow down the reaction that produces the carbocation, means that yes, so you will also have similar to a mercurium ion. But we are not really going into the details for this reaction. So the only thing that we need to know is that it creates an enol, the one which is not isolated. Why? Because enols are compounds that are not stable. They are more stable in their keto form. That's why you get a ketone. Okay, so It's gonna go. This one is the keto-enol tautomerization. That's the one that we have to understand. I will explain when I do the mechanism. What is tautomerization? Okay, so the enol and the ketone are tautomers of one another, and then the equilibrium favors the keto form. Why? Because the ketone is more stable than the enol. The hydrogenation is the opposite, is the anti-Markovnikov, and this one is regioselective, meaning that that's the only product. Here it is, doesn't really say anything about selective or specific. Here is selective, meaning that the major product is going to be the anti-Markovnikov. So here we use the same reaction conditions that we used in the past, right? If you guys recall for alkenes, BH3, THF, hydrogen peroxide, sodium hydroxide. You also get an OH, an enol, right? This one is also called an enol. Why is it called enol? En is for the alkene, and ol is the alcohol. It's an alkene with an alcohol. So that's what it means, the word enol. But the enol is unstable. It goes to the keto form. In this case, the keto form is not a ketone, it's an aldehyde. Okay, so just be careful. Just remember that part. Now, something that you guys will see a lot is that they say that if you use plain BH3, the reduction can happen twice or even 3 times, right? When we recall the mechanism for hydroboration that we did in chapter 8, the borane has 3 H's to react, right? That might be an issue. Why? Because the enol that you produce also has an alkene. So maybe the borane, BH3, can do a second addition, right? That's what it says, to prevent the second addition. Why? Because it has 3 BHs. So to prevent the triple reaction, that's why they use dialkyl borane. So dialkyl boranes, they have only 1 BH, not like borane, right? That has 3 BHs in this case. So with this, they can control the reactivity of the borane. So in this case, they use NiBBN. BBN is going to be used only for alkynes. Just keep in mind, only for alkynes. You don't want to use that for alkenes. For alkenes, you want to use the plain BH3. For alkynes, you guys want to use NiBBN. Okay, so that's the most common. That is the bora bicyclo 331 nonane. That's the one. The other one is dicyamylborane. Dicy. What is that? Well, that name is kind of like weird, right? Dicyamylborane, right? So, but the one that you guys will see a lot in the books is NiBBN, so which is the bora bicyclononane, right? Bora bicyclo. BB is bora bicyclononane 9. Okay, so bulk acidic groups provide steric hindrance to prevent a second addition. Yeah, that's why the bicyclic compound is preferred. So you will see BBN for alkyne, right? Alkyne hydration. BH3, what if I see BH3 with alkyne? Should I still proceed? Yes, you still proceed. You will also obtain it. But technically, no. Because it might give you a second addition, but you guys, just use it. You see it. But you can also see BBN, NiBBN, as an alternative and not diactyl borane, which could be actually a more appropriate, right? A more appropriate reagent. So just as a summary, before I go to the explanation on the paper, for a terminal alkyne, you can use, right? It doesn't make sense to use this reaction for an internal alkyne, because in internal alkyne, there is no Markovnikov, anti-Markovnikov. In an internal alkyne, both ends are Markovnikov, right? So in that case, you will get a mixture. But for a terminal alkyne, it makes sense to use this reaction. Markovnikov will produce a ketone, and anti-Markovnikov, meaning the hydroboration, will produce an aldehyde. So here we have a summary. You have an alkyne, use right? The acid catalyzed hydration, you get a ketone, and you use hydroboration, you get an aldehyde. Okay, so now after that, I'll just go ahead with the ketoenol. So let's go over the acid catalyzed. Right? What happens in the acid catalyzed reaction? The acid catalyzed uses sulfuric acid, water, and mercury sulfate. That's a catalyst. The mercury sulfate is the catalyst for my reaction. So that is a Markovnikov reaction. So if I have an alkyne like this, I'm going to use butane, right? Butane, this is butane 1, 2, 3, 4, butane. If I use this reagent, right, acid catalyzed hydration, it will do the Markovnikov. There is no question about the Markovnikov. It will add OH to the Markovnikov side and H to the anti-Markovnikov side, right? So H and H. So what we get is OH here and H there. So you see, dehydration happens because you're consuming only one pi bond. The second pi bond is intact. I don't touch it. So technically the same thing happens as we did it on chapter 8 when you guys were doing oxymercuration. There is no carbocation, there is no CCR because the mercury prevents that, right? Forming most likely the mercuridium ion. We don't need to know the mechanism. But here you see the hydration, Markovnikov produces an enol. Once again, why is it called an enol? It's an enol because I have the ene, the alkene, and the ol, enol. Actually, these compounds are also a functional group. And you guys will do the chemistry of enols and enolates, enols by the end of chemistry 240. It's very important, the chemistry of enols. But enols are unstable. They're very reactive, mostly if they are in acidic or basic conditions. In the case of acid catalyzed hydration, I have the acid. Therefore, the acid will make the enol more unstable. It's going to be transferred, or it's going to be migrated or tautomerized to a ketone. Where? Well, it's in the same, right? The same Markovnikov point. The Markovnikov carbon will becomes double O. So wherever you guys have the alkyne, the Markovnikov carbon is going to get the C double O because you are using the Markovnikov hydration, which is the acid catalyzed. If you do the other one, the hydrogenation, you will get the C double O on the anti-Markovnikov carbon, which will be this. But let's go over first the Markovnikov, which is the acid catalyzed. Okay, so how is that happening? That OH, right? That conversion. Why is my enol? Let me see. Why is the enol unstable in acidic conditions? The mechanism is right here. We need to know this mechanism. Okay, so as any alkene is electron rich, here oxygen is also electron rich, but alkene is most desperate from because of the electron repulsion. It will attack the H. That H, of course, it's gonna go to it's gonna create the most stable carbocation, meaning that it will go there. The H is added to that carbon. The carbocation will go internal, right? Because remember, it's a Markovnikov type of addition to the alkene. Now, who is gonna help this this particular carbocation? I have electrons from the oxygen. That is resonance. Okay, this part is resonance. The OH helps to compensate that plus, that carbocation, by donating. And then who comes? Water. Water comes to eliminate that particular H. That's why they call it acid catalyzed, because this one only catalyzes the reaction. Okay, the keto, this is the enol form, and this is the keto form. Keto-enol tautomerization. Okay, now what is tautomerization? In this case, this keto and this enol, these are called tautomers. The process is called tautomerization. Tautomerization means that it is the conversion of two isomers, okay? That two isomers can be converted by just moving or shifting a hydrogen. The position of a hydrogen is shifted by a chemical reaction between two species or two isomers. Okay, once again, what are tautomers? Tautomers is not enantiomers, is not conformers, is not diastereomer, no. Two tautomers are compounds that they have the same formula, and the only difference is the position of a hydrogen. So you see, here it has two H's, here you have two H's, here you have three H's, here you have one H, here you have zero H's. So see, the only thing that we did was move this hydrogen from here to here. That's all. But how did I do that? Through a chemical reaction. So a chemical reaction must be involved in the conversion of a tautomer from the other tautomer. These two are isomers, but the conversion of two isomers that involve a hydrogen shift through a chemical reaction. That is tautomer or tautomerization. The process is that. Remember that I might be asking that in quizzes and exams, okay? Any semester. Okay, good. So that one is the mechanism in acidic conditions. We will also do the same thing in basic conditions, okay? So in acid catalyzed, that's what we get. I'm gonna give you some other examples, okay, for acid catalyzed. Let's say that I have this particular alkyne. If they tell me, okay, so let's do sulfuric acid, water, mercury sulfate. So this one is my Markovnikov carbon. Okay, that's my Markovnikov. So technically, I should produce that compound. That should be my final product. What is that carbon? This carbon is right here. Just put the C double O in the Markovnikov, right? On the Markovnikov carbon. That's all. Is that the real product? No, the real product is the enol. That's the enol. But as we know, the enol is not stable. The enol will get converted in the keto form. So really, should I show this or should I show this? You should show this. This is more stable. Is it wrong if I show this? No, it is not wrong, but you will get points off because the enol is not the most stable form, right? So let's say now, oh, what about if I have a compound that has no Markovnikov? Okay, so in that case, if you guys do the acid catalyzed hydration, you guys will have two products, right? Because here, this reagent cannot distinguish between the Markovnikov and the anti-Markovnikov. This is the Markovnikov and this is also Markovnikov. Then you will get two products, one in the red and one in the black carbon. If you get the one in the red, 1, 2, 3, 4, 5. Okay, 1, 2, 3, 1, 2, 3, 4, 5. You will get in the 1, 2, 3 red, 1, 2, 3 red, 1, 2, 3 red, and then this is black and this is black. One in the black and the red dot, and another one on the black dot. You will get two products here. What if the products are the same? Yeah, in this case, you will get only one, right? So let's say that if your alkyne is symmetrical, right? So this alkyne is not symmetrical, for example. You will definitely get two products. But if your alkyne is symmetrical, meaning an ethyl here, yeah, in that case, you get only one product. But here, the alkyne is not symmetrical. You will get two products, okay? So make sure that you guys remember that. I mean, if you guys have an alkyne that is internal, you have to show both products, both potential products. Okay, if the alkyne is not symmetrical. If the alkyne is symmetrical, you will get only one product. Okay? So for example, in a ring, can I also do that in a ring? Yes, you can also do that in a ring. So in this case, if I do the reaction, there is no Markovnikov here, right? So same thing. So I will get a ketone here and also a ketone here. They are the same thing. So they're the same. So I only get one single product. You don't have to show both because both of them are equivalent. Why? Because this alkyne is symmetrical. Okay, good. Now let's do the next reaction. The next reaction is the hydroboration. It's also hydration, but it's anti-Markovnikov. Anti-Markovnikov means that it goes to the least attitude. So if I use this butane, right? I use this chemical combination, BH3, DHF, hydrogen peroxide, sodium hydroxide, right? So if I use that, my anti-Markovnikov carbon now is this one. So I should get the OH added there. The OH is added to the anti-Markovnikov. Right? The OH, because it's a hydration. But this one is an enol. Enols are not stable. They are more stable in the keto form. That's the keto form. Oh, but professor, this is not a ketone. This is an aldehyde. Yes, but it's called the keto form. The keto form can come in two functional groups, ketones and aldehydes. Remember, keto is not the same as ketone. Ketone is one of the keto forms. Aldehyde is another keto form. Is keto form. Okay, the keto and the ketone aldehyde, those two are keto forms. Aldehyde is one of them. Okay, now how is this conversion? Remember, it's anti-Markovnikov. It produces aldehydes. This one is an aldehyde. Okay, so how is that happening, or why does it happen? I don't see acid. No, we don't see acid. But remember, the keto-enol tautomerization occurs in acid or basic conditions. Do I have acid? No, I don't have acid, but I have base. I have sodium hydroxide. That is the base that is going to be acting here. How? OH minus. This OH, I shouldn't have written it differently. Just give me a second. Okay. That OH is acidic because remember, it's an alcohol with resonance. Alcohol with resonance definitely will be more acidic. So that OH will deprotonate the oxygen. Creating what we call an enolate. It will deprotonate it. What happens now? What happens is that it also undergoes resonance. That's why hopefully we remember resonance. There is a conjugation, right? Negative charge, single, double. That's resonance. The resonance combination would be okay, minus there. This carbon is the minus. And now comes water. Water is everywhere. The C minus, the protonates the water. This guys get this, right? So that's the H that was not written, but it should be there. That hydrogen, and you get the aldehyde, which is a keto form. So that's the tautomerization enol keto form. But in this case, the keto form is an aldehyde. These are tautomers in basic conditions. Do I need to know basic tautomerization and acidic tautomerization? Yes. You guys have to know both tautomerizations that are right that accomplish right the conversion the enol to the keto form to produce aldehyde or to produce ketone. Right. So let's do some examples for this reaction. Okay? So some examples. Let's say that I have terbutyl. Okay, that one. That one I can clearly see which one is Markovnikov, anti-Markovnikov. Let's use NiBBN, right? That was another one, an alternative. NiBBN, hydrogen peroxide, sodium hydroxide. Okay. NiBBN is a hydroboration reaction, right? We said that we will use that a lot. So anti-Markovnikov means that you guys will get the aldehydes or the COO in the least attitude. Okay, so I have it there. And that's my carbon, right? 1, 2, 3, 4, 1, 2, 3, 4 aldehydes. Can always check and then count the number of carbons, right? From the reactant and the product. What if I don't have an Markovnikov, right? Or a terminal alkyne? Can I still do hydroboration? Yeah, you can still do hydroboration. It's only that you will get two products. Okay. Anti-Markovnikov here, anti-Markovnikov here in red and in black. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. 1, 2, 3, red, 1, 2, 3, red, 1, 4, black, black. Okay. Double O on red, double O on black, 2 ketones. Oh, I thought that hydrogenation produces aldehydes only. Yes, it produces aldehydes only if you have a terminal alkyne. But if you have an internal alkyne, it also produces ketone. So if you have an internal alkyne, it doesn't really matter if you guys are using hydrogenation or if you use the acid catalyzed, because there is no difference between Markovnikov and anti-Markovnikov. So both reactions will give you exactly the same product, but not if it's terminal. If it's terminal alkyne, yeah, you guys have a Markovnikov and an anti-Markovnikov site. All right. For rings, it's the same application. So there's really no difference between rings. It's very similar to what I showed you before for the previous example. All right. So that concludes the hydration reaction. We need to know those mechanisms, right? Remember the mechanisms for the keto-enol tautomerization. Good. The halogenation is very easy, very straightforward. It's used for to produce a tetrahalide. So in this case, we use always excess of the halogen. You can use chlorine and bromine. Iodine, no, apparently, because it's too big. Iodine is too big because of the static hindrance. It's very difficult to have 4 iodines, right? In adjacent or contiguous carbons. So you only can use bromine and chlorine, 60 to 70%. And it's a trans addition. So first, that means that you add this this halogen with this halogen. And then you will start adding this halogen, and this halogen is trans. Okay, so that's what it happens, right? One equivalent of the halogen, you get a trans alkene, and then minor cis alkene. That's the selectivity. But then if you keep adding excess, right? Of course, you will get the full halogenation, right? So you will get another one here, another one here, and another one here for a full halogenation. So it depends if it's one equivalent or if it's excess, right? The mechanism for alkyne is not fully understood, so they don't really know if it's really through the bromonium ion. So many things for the alkyne are kind of inconclusive. Why? Because they have a short life, so the reactivity is really high. So the reactions are so violent, or they are so fast, that it's really difficult to time it, even at low temperatures. It's because of the reactivity, right? Okay, next reaction. Okay, so far, how many have we done? Let's go back to the list. We did this, acid catalyzed hydration, hydrogenation, oxidation. Now we did already halogenation for equivalence, right? We have done those. So we're only left with ozonolysis and alkylation. So let's go. 2 more reactions. Ozonolysis, no mechanism. All we need to know is that ozone also cleaves alkynes. Remember that on chapter 8, we use ozonolysis to cleave an alkene, right? And then we were using a combination ozone in DMS, right? Dimethyl sulfide, or zinc in water, right? In this case, no. In this case, it is ozone in water, and it oxidizes all the way to carboxylic acid. Okay, so what you guys are gonna do, we're gonna break the alkyne in the middle, and then you will put carboxylic acid in both ends. Okay. Once again, remember that for this chapter, you're also having your reaction and listing what is the functional group that you're producing. For example, ozonolysis is used to produce carboxylic acids. Halogenation is used to produce dihalides or tetrahalides. Hydration in acid catalyzed is used to produce ketones or aldehydes. Same thing with hydrogenation. Hydrogenation is used to produce alkanes. Partial hydrogenation is used to produce alkenes from alkynes, right? So every reaction has a purpose. So you guys have to come up with a table. I will show you a table at the very end that that you guys will learn how or retain or get very familiar with the reactions and also what you are producing. Remember, that's important for the synthesis. What to do if you guys have a terminal alkyne? If I do ozonolysis, you do ozonolysis, what you get is carbon dioxide. This particular carbon becomes carbon dioxide. That's only for terminal alkynes. Something that is very important also to keep in mind is that this reaction of ozonolysis shortens the chain, right? Since you are cutting the compound in half, right, or in the triple bond, you're always going to have less carbons. So that's very important for your synthesis purposes. If your product has less carbons than your starting material, most likely you guys are using ozonolysis at some point. Okay? So for example, 5 carbons to 3 carbons. Okay, if I'm going from 5 to 3, I had to cut it at some point. So what are the reactions that allow me to cut a molecule? Ozonolysis is the only one that we have learned so far. Now, is there any reaction that allows me to elongate my chain? Yes, that's the next reaction that you can make the chain longer. Okay? But for ozonolysis, remember this produces carboxylic acid. If you have an internal alkene, internal alkyne, you get 2 carboxylic acids. You have a symmetrical alkyne, that would be perfect because you get only 1 product. And if you have a terminal alkyne, you get a carboxylic acid and carbon dioxide. Okay? So that's very important for you guys to remember. For example, predicted product for the following reaction. In this particular case, I have a symmetrical alkyne, right? This half is the same as the other half, left and right are the same. So if I do ozonolysis in water, I cleave here. So I will have my compound like this. Here, the triple bond used to be here. So on this carbon, I will have a carboxylic acid. What is this carbon? This carbon is right here. And on the other side, I will have the other carboxylic acid. But since these 2 molecules are the same, I have only 1 product, 2 of those cyclopentanoic acid in this case. Okay. Ozonolysis of symmetrical alkynes is particularly useful to produce or to prepare carboxylic acid. Only 1 product is formed, 2 equivalents of it. Okay? So this carboxylic acid is is the only reaction that we have learned that produces carboxylic acid. So be very, remember that reaction. Last reaction, alkylation. Okay, so in this last reaction, we will use the property of the alkynes that are nucleophilic when they are deprotonated. So we have an alkyne. We deprotonate the alkyne with amide to form the alkynide ion. The alkynide ion is nucleophilic. As it says here, alkynide ions are good nucleophiles. So they can react in an SN2 reaction to produce an alkene, an internal alkene. So if this one used to be a terminal alkyne, now you're producing an internal alkyne. Of course, you can do many things with this alkyne later on, right? So, but the idea is to make it longer, right? So for example, here you started with five carbons here, right? So 5, here would be 7 carbons. Then after this reaction, maybe you can end up having 12 carbons. You are elongating your chain. This reaction is never going to be shorter in number of carbons. You're always going to be longer. More carbons will be added. How many carbons? Depends on that R group. Maybe this R has 1 carbon, 3 carbons, 10 carbons. That doesn't matter. But you're elongating the chain by adding that alkyl halide. Does it have to be an alkyl halide? Yes, has to be an alkyl halide. It can also be a tosylate. Yeah, that's fine, tosylate, because tosylates are also good leaving groups that they are good for SN2 reaction. Can I use the protonated alcohol? Like if you remember the protonated alcohol, OH2+, which is also a good leaving group? No, you cannot use that. Why? Because you are working with alkynide ion, is an anion. So if you use this compound, it will deprotonate it. The alkynide will deprotonate this guy. You don't want that. You want to attack the carbon. You don't want to attack the hydrogen. You want to attack the carbon. So don't use this. Don't use the protonated alcohol in this particular reaction. Tosylates are good, and any alkyl halide. Iodide, bromide, chloride are good. Okay? So this is an example. For example, in the first case, you have an alkyne. You deprotonate it with sodium amide. That sodium amide, right, gives you the alkynide, right? After this step, you guys will get a minus there, and that minus will attack the iodide in an SN2 reaction. You will add 2 carbons. That's the new CC bond. The good thing of this reaction is that definitely it will be maybe one of the first reactions in which you guys are making a CC bond. You have no idea how important and how crucial it is in organic chemistry to make a carbon-carbon bond. So far, you guys haven't done it, except the cyanide, but it's very important. All what you have been doing is maybe adding a chloride, adding an OH, adding a sulfite, right? Adding a nitrogen. But making CC bonds is very important because they have a high stability. They're very spontaneous. It's a very strong bond. And so that also is one of the importances of this particular reaction, that you're making a CC bond. Acetylene, as I was telling you at some point, acetylene is the one that we will use it a lot in synthesis. Why? Because acetylene is a double terminal, right? You can see acetylene has two terminal CHs, triple bonded. So that means that you can alkylate this way, or you can also alkylate this way. That's what they do in this example. You have acetylene, you deprotonate it with sodium amide, then you add the first alkyl halide, you add it. Now you deprotonate again. Now you deprotonate the other alkyne, and then you add a second alkyl halide. You can get two R groups attached to the alkyne, to the acetylene. And so that's why acetylene is so convenient for in terms of synthesis. Here's an example with a real molecule. Okay, complex target molecules can be made by building a carbon skeleton that you convert in a functional group. Here we have the summary for chapter 9. Here, this chapter 9 is going to tell you all the reactions that we learned today. So the very beginning that we learned is how to make the alkyne. The alkyne was done through elimination. You can do the elimination using geminal dihalides, or what are the vicinal? The vicinal. Okay, the vicinal, right? Vicinal dihalides. Those with sodium amide, right? You can convert it to alkyne. Now you can also do hydrohalogenation. Hydrohalogenation, you guys will go this way, right? So this one is in excess, this one is with only 1 mole of HX. Hydration is here, hydration Markovnikov, hydration anti-Markovnikov, good. Halogenation, one equivalent, partial dihalogenation, and then you use excess, you get the tetrahalogenation. Ozonolysis gives you carboxylic acid. If it's terminal, it will give you carbon dioxide. If you want to elongate it, you can use the alkyne, sodium amide, and the alkyl halide to get an elongated chain. Now, any alkyne can be reduced either with CHE230 if you want to go all the way to alkane, or you can use a partial reduction. Two ways to do the partial reduction. If you want the cis alkene, you use the hydrogen in Lindlar's catalyst. And if you want the trans alkene, you will use sodium in liquid ammonia. Okay, so take this one. That will be your second chart, right? Scheme. We have a one very similar for chapter 8. So print it out. You won't be able to use it in quizzes and exams, but have it with you. So have it everywhere you go, any free time that you have. Please get familiar with those reactions. You will definitely need them for the synthesis and even for the reaction questions. More synthesis, that's one way. Here is how to convert, right? Halogenation, it is to produce alkynes. Don't forget that one way how to produce alkyne, you have to start from an alkene. There is no other way you can make an alkyne, right? So it has to go from an alkene. That's the starting point. Anytime that you guys need to do a reaction with alkynes, you have to prepare the alkyne most likely. How can I prepare the alkyne? From alkene. How do I prepare it from alkene? You do a dihalogenation of alkene. You get the vicinal dihalide, and then you use the excess sodium amide in water to produce the alkene. Here are some the reductions, right? It's very important to do the reduction. And I mean, we will do some examples for synthesis. And for synthesis, right now I'm going to be offering four reactions, okay, 4 different approaches. Definitely, I will have more examples in the solve problem videos. But also, I mean, you guys have the all exams and the practice exams. Definitely, you will see some other example for synthesis. Okay, so right now there is no more to show on these slides. I'm going to stop sharing. So we're done. So we'll do some practice for synthesis problems. Okay, so in this particular problem, they are telling me like accomplish the following conversion. My starting material is a trans alkene, and I have to get the same length in a cis alkene. What reaction allows me to produce selectively a cis alkene? So that's something that you, anytime that you guys are here in a synthesis question, you always have to think, okay, so what allows me to do a cis alkene? Okay, I know that if I have an alkyne, let me say, to make a mistake. If I have an alkyne, let's make it simple. If I have an alkyne, I use H2 in Lindlar's catalyst I can produce a cis alkene. Okay, so that's the cis alkene that I need, right? Okay, so that's the only way. Is there any other way how to produce cis alkene? No, there is no other way. Selectively cis alkene. Yes, so it has to be H2 in Linglar's catalyst. Do I have to write the Linglar's catalyst, the whole full name? At least Linglar's. You don't have to write catalyst, just Linglar's. Okay, so what is the starting material for cis alkene from the Linglar catalyst? Has to be an alkyne. So how long is this? 1, 2, 3, 4. So I need an alkyne that is 4 carbons long. Okay, 1, 2, 3, 4. Now, can I go from here to here? Am I doing any elongation? 1, 2, 3, 4. 1, 2, 3, 4. No, no elongation. So good. If there is no elongation, that means that I don't need to do any, right? Any alkyne ion. So I just have to convert this alkene into an alkyne. How can I convert an alkene into an alkyne? That was one of the reactions in the second, in the last slide, right? Very important. How to convert an alkene to an alkyne. The step one that they were proposing is that first you have to halogenate it, Br2. If you halogenate it, you guys will get bromine and bromine. Okay. Dihalogenation. Now I have to do a elimination, double elimination. How can I do the double elimination? Excess sodium amide followed by water. Do I need water? No, because it's an internal alkyne, so I don't need water. If it's a terminal alkyne, yes, I will need water, but I don't need water. Here, it's just excess amide. That's all. I will get this particular compound, and then we need a catalyst, I will get that compound. Okay, so you follow this. Alkene, transalkene, that's fine. Bromine is a dihalogenation. No mechanism, just do the reaction. It's a trans dibromine. And then that bromine with excess Mi will do a double elimination. This bromine goes with this hydrogen, and this bromine goes with hydrogen, forming the alkyne. I don't need water because it is not a terminal alkyne. And then this alkyne that I just produced, I do hydrogen in Lindlar's catalyst to produce this cis alkene. How many steps for this synthesis? 3 steps only. That's the average that you guys will see. Next mechanism. Okay, so I have this compound, and the product is a tetrabromination. Tetrabrominated. What reaction allows me to tetrabrominate? Out of all the ones that we have seen in chapter 7, 8, and 9, the only one that allows me to tetrabrominate is the one that has an alkyne and uses excess bromine, and I can get the tetrabromination. That's why I was telling you guys that it's so important to know the reactions. If we don't know the reactions, I can't do this. Okay, so if you have the sheets with you, of course, you can do it. At the beginning, I would recommend you to practice the synthesis with the 2 sheets in front of you, right? The one from chapter 8, the one from chapter 9. But little by little, stop using it. And then until you are working on your own, you remember the reactions. Definitely start with them. So that's why I have it as part of the PowerPoint slides, for you guys to have it. So have it as a reference at the beginning. Do as many practices. Once you get used to those reactions, then slowly you will just like get rid of them. And then you guys have to do the reactions on your own. I know it takes time, and time is the least that we have these days, right? But I mean, we have to get used to it. I mean, it doesn't, I know it's a pain. 10 reactions in chapter 8, apparently 12 reactions in chapter 9 is a lot. I know. But I mean, let's make an effort. We're almost done with this semester, so let's see how we go. Okay, so I have this tetrabromination. That means that I have to start from an alkyne. So this reaction, I had to use bromine, excess bromine, right? So what was the starting material? The starting material had to be an alkyne. 1, 2, 3, 4. Okay, so my alkyne was this. Okay. 1, 2, 3, 4. Yes, right? 1, 2, 1, 2, and then here is with the alkyne. The alkyne used to be here. right? On that bromine. Now, how do I make the alkyne from this compound? We know that the only way how to make an alkyne is from an alkene, right? We said that at the beginning. But do I have an alkene? Unfortunately not. Can I make an alkene from this? Yes, I can make an alkene from an alkyl halide. How? With an E2 reaction. In an E2 reaction allows me to make it convert into an alkene. Why do I need to make an alkene? Because I need the alkene to make the alkyne. There's no other way how to make alkynes. It has to be from an alkene. Okay, so why the alkene? Because the alkene will take me to the dihalide, and the dihalide, with double elimination, I can go to alkyne. That's the path. Okay, so where do I need the alkene, right? Do I need it here or do I need it here? Apparently, I need it terminal, right? Because my alkyne is terminal. That means that I want my alkene terminal as well. The alkene terminal means that it's going to be a Hofmann elimination. This one is a Zaitsev. I need a Hofmann alkene, not the Zaitsev alkene. So with the Hofmann alkene, the only base that I can use is terbutoxide. If I use terbutoxide, I will create this alkene. Good. At least they look alike. 1, 2, 3, 4. 1, 2, 3, 4. Terminal. Terminal double bond, terminal alkene. So here now is the same approach that I had here. So I will do a dibromination or dichlorination, doesn't matter. But honestly, I have seen more bromination than chlorination. Bromine. And then from here to here, I have to do the double elimination. That means excess sodium amide, right? Remember sodium amide, excess sodium amide. Now, do I need water? Yes, in this case, I do need water because I'm preparing a terminal alkyne. So step 1, excess sodium amide. Step 2, water. Now I do need it. Here, I didn't need it because it was an internal alkyne. But here, I need it because I have a terminal alkyne. Okay, so if I have this compound, terbutoxide will give me the Hofmann alkene. Then I do bromination, and then I do the excess amide in water, and then I get the alkyne. The alkyne, I do excess bromine, and I get the tetrabrominated compound. Good. We'll have more examples of that later. All right, next conversion. Okay, carboxylic acid from an alkene. Good. Carboxylic acid, what reaction allows me to produce a carboxylic acid? Okay, I know I learned a reaction that says that alkynes with ozone in water produce carboxylic acids. And this reaction can be in 2 ways. If it's terminal alkyne or internal alkyne. If I have a terminal alkyne, I get 1 carboxylic acid and carbon dioxide, shorter in the chain, right? And then if I have an internal alkyne, I get 2 carboxylic acid. So in this case, I need to get only, they're telling me this carboxylic acid. Okay, so first thing to do is like count 1, 2, 3, 3 carbons. Good. What about here? 1, 2, 3, 4 carbons. Okay. What is this telling me? This is telling me that my chain is getting shorter from 4 carbons to 3 carbons. That means that this molecule, it has to be cleaved, right? At some point, right? And then it makes sense because I have 1, 2, 3 double bond, 1, 2, 3 carboxylic acid. That means that I'm cleaving my molecule here. I will never imagine that I'm cleaving the molecule here. Why? Because there is CC bond. C double, which one is easier to break? A C or a C double C? A C double C, because there are reactions that allow me to break this, right? So to cleave or to create carboxylic acid in ozonolysis, the starting material for an ozonolysis is an alkyne, okay? So let's do it from an alkyne. I have O3 in water. Now, how is gonna be my alkyne? If I know that my starting material has 4 carbons, so most likely my alkyne also has 4 carbons. I would never imagine an alkyne that has 10 carbons, right? If my starting material has 4. So if this one has 3, I can do this one with 4 because I have to shorten it somehow. If this one has 4, so most likely my alkyne is also 4 here. If this one is 5, that means that this one has to be 5. Okay, makes sense? If this one is 6, this one has also to be 6. All right. So carboxylic acid, I have the alkyne here. Now, how do I make an alkyne from an alkene? Well, we know that already. That should be a routine. Alkene, I use bromine, dihalogenation, and then I do double elimination. Step 1, excess amide, sodium amide, and step 2, water. Why? Because I am producing a terminal alkyne. Terminal alkyne needs water for the final protonation. Good. So bromination, let me erase this so you guys can see it well. Bromination, dibromide, excess amide in water produces the alkyne. And then here I do the ozonolysis. Now you say, like, oh, but professor, here you also produce carbon dioxide. Why is carbon dioxide not part of the product? That's fine. Sometimes when you guys produce two products, they only mention one. They don't have to mention both products. Only with one, that should be enough for you guys to follow this path. Okay? So even if in the keto form, right? The hydration, that you have the enol and the keto form. Yeah, I mean, in that case, for example, if in a hydration reaction, when you cannot distinguish between two ketones, right? In that one that we had here, let me find it. Okay, right here, for example. This reaction, these are two different. This reaction produces two products. But what if I make a synthesis asks me, produce this? Can I use this? Yes. Oh, but I produce this and this. Yes, but your goal is to produce this. As long as you produce it, that doesn't matter which one is the secondary or the byproduct. You can use this reaction because this reaction is taking you to this molecule. So you are allowed to use it, even in the presence of something else. Okay? So that's something that you guys have to keep in mind, that if you have multiple products for a reaction, you can use it for a synthesis, even if it's a side product. And the last one, the last synthesis here we will use the elongation. You can see that it's an elongation reaction. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6 carbons. 6 carbons versus 4 carbons. Here, I'm definitely doing an elongation. Okay. So what is the elongation? Well, I'm adding 2 carbons. What reaction allows me to elongate a chain by a given number of carbons? Is the reaction with the alkanite ion. You have the alkanite ion, and if you add a reagent, which is alkyl halide, you guys can add that reagent, right? That number of carbons to your chain. Okay, but this reaction gives me an alkyne. I don't get an alkyne. I'm having an alkane. Okay, so if you're having an alkane, that's fine. I mean, why? Because the alkyne can be reduced with H2PT to an alkane. Okay, so that is the strategy. So first you have to identify, okay, I'm elongating my chain. Yes, I'm elongating it by 2 carbons. Okay, good. The only way how you can elongate a chain is with the alkyne ion. With the alkyne anion with alkyl halide, you get the longer chain. And then this longer chain can be reduced with H2PT to an alkane. That's what we're going to do. Okay, good, makes sense, right? So this particular approach. Okay, so in this case, I can go forward. So I know that I have to form the alkyne ion. How do I make the alkyne ion? With sodium amide. You use sodium amide, the alkyne gets deprotonated, minus there. And then I need to use the alkyl halide. How many carbons do I need to add? I need to add 2 carbons. So I will use ethyl iodide. The alkanide will attack in an SN2 reaction to produce this alkyne. Right? Now it's 1, 2, 3, 4, 5, 6 carbons. Oh, how, okay, yeah. I was gonna show the mechanism because I told you that the alkyne ion mechanism is gonna be right part of the chapter. Yeah, in this case, what you guys do is that I'll use this reaction. The amide will steal the H, form the alkanite. The water is an spectator, right? Sorry, the sodium is an spectator. So the amide will extract the hydrogen. This bond goes to the carbon, forming the alkanide. And then the alkanide does an SN2. That one has to be an SN2. Remember the arrows for the SN2, one side and the other one for the opposite side. And you guys get the alkyne. Now they have the alkyne. From this alkyne to alkane, all I have to do is H2PT. And it gets rid of the triple bond to go to the single bond. And that's it. That's it, this mechanism, this synthesis reaction. Okay, so here the synthesis also helped me to do the mechanism for the alkanide elongation. This is how it gets elongated to a product. That's the mechanism. I will do more about that. I mean, about this reaction for the solve problem videos. Okay, so keep an eye on those reactions, and then let me know if you guys have questions regarding this particular chapter. We're almost done, guys. One more chapter to finish Chem 230. Yes, please keep going.